Okay, so today we will start gate topic electronics, and today we will talk about 5 questions of electronics from 2000, I think 23, 22 and 2018 or something. I will take the class, questions. So today we are just going to start electronics topic of gate. Can you hear me properly? Yes? Okay, fine. So, yeah, let's start. So, the first question is from GATE 2023. Okay, and I am just taking the GATE question of question number 24. So, let us first ask the question. What is the question here? Which one of the following options is correct for the given logic circuit? And what is the circuit here? The circuit is given here that P, Q are the inputs and X is the output. And there is some gates are given. And they are asking that which one of the correct option for this gate circuit. And what are the options? The options are like P equals to 1, Q equals to 1. In that condition, X will be 0. This is the first condition. The second one is P equals to 1, Q equals to 0. Then at this condition, X will be 1. Then similarly, P equals to 0, Q equals to 1, X will be 0. And the fourth one is P equals to 0, Q equals to 0, X will be 1. Okay. So there are 4 options and we have to choose which one is the correct option. So let us calculate. Okay, so first of all I am just going to draw the circuit whatever it is given here. Like that, okay. So there is P, Q, then there is one AND gate. Just we have to think a little bit. It's a very simple question. So what we will think? We will think about this gate properties. What is the Boolean algebra? What is the logic gate properties for these gates? So this is AND gate, right? This is NAND gate. This is OR gate. So what we will write? Just let me first draw that one. It is like this. Then it is like that. Then this. This is P, Q and X. I have just written a little bit tilt, but yeah, fine. So this is P, Q and X. So first of all, I think all of you know all these things, that what is the properties for the gate, that means AND gate, OR gate and NAND gate. But still I am just going to write it little bit. So let me check about AND gate first. So AND gate, for AND gate, let us our inputs are P and Q, and let's, okay, there is something. Oh, option D. Okay, you have already written that one. Very good. I think option D is, yeah, option D is correct one. So, okay, so if you all know these properties, then I am not going to explicitly explain these properties, but yeah, like I am just going to write here. If there is a 0, 0, then output will be 0, 0, 1, output will be 0, 1, 0, output will be 0, 1, 1, output will be 1. It is for AND gate, right? And for OR gate it will be what? P, Q, Y, 0, 0, 0, 0, 1, 1, and then 1, 0, 1, 1, 1, 1. Fine. Now coming to NAND gate, as it is there in the option. So P, Q, Y. So 0, 0. 0, 0 was 0 for NOT gate, but it is an AND, that means it will be 1. So 0, 1, it was 0, but here it will be 1. Then 1, 0, 1, 1, 1, 0, like that. Okay. So if I just put these conditions here, let's say I am talking about D, as already one of the student already gave the answer that it will be the correct answer as D. So what we will do, we will just directly calculate D option first. Is it correct or not? We will see. So what is D here? D means P equals to 0, Q equals to 0, X should be 1. Okay, let me check. So P equals to 0, Q equals to 0. So if P equals to 0, Q equals to 0, then you can see that 0, 0, NAND gate, sorry, it is AND gate, that means it will come as 0, right? Now this P is coming here and it is 0, 0. These two inputs are same as P, so it is 0. So if 0, 0 is coming as input and in a NAND gate, then it will be 1. Then this 1 is going here and this 0 is going here. So 1 and 0, it will become 1 because it is OR gate, right? So if I have P equals to 0, Q equals to 0, then our H should be 1. You can see here, this is the correct option, D. Now if I just calculate, let's say arbitrarily B option, and we will check that it is correct or not. P equals to 1, Q equals to 0, X should be 1. Is it correct or not? P equals to 0, X is 1. So if it is 1 and this is 0, then also it is 0, right? And this 0 is coming as here, 0, 0, and this 0 will give you 1. So as a whole, it is coming as 1. But you can see that, oh sorry, Q equals to 0. What? Oh, sorry. I think I have taken the wrong option. Let me take one more option. D option is correct, right? We have already calculated that D option is correct one. Now I am just taking the B option randomly. P equals to 1, Q equals to 0. P equals to 1, Q equals to 0. So if it is 0 and it is 1, then this one will be 0. If it is 1, then it will come as 1, this will come as 1. And if it is 1 and 1, then it will be 0. Then you can see that this 0 and this 0 is coming, so our output should be 0. But in the B option, it is showing that our output is 1. So that means that will not be the correct option. Similarly, if you just go for the A and C option also, you can see that these are not the correct one. Okay. Okay, so I am just taking the C option also again, so that it will be simply useful for all of you. Yeah. So what is C option? C option is P equals to 0, Q equals to 1. P equals to 0, Q equals to 1. So if it is 1, it is 0, then also it is 0. Now this 0 is coming here, so 0, 0. This 0, 0 will go as 1. So this 1 is coming, this 0 is coming. So this will be 1. Because it is OR gate, right? So our output should be 1. But you can see that for P equals to 0, Q equals to 1, output is giving as 0. So that means it is also not correct. Okay. So similarly, you can check the A option also. So as a whole, we can see that the correct option is D. I think it's very simple and it can be understandable by all of you, right? So if it is understandable, then we can go to the next question. Okay. So this is the next question, and the next question we have taken from GATE 2022 question paper, and the question is question number is 28. Okay, so this is a multiple selection question. That means there will be more than one question can be correct one. Okay, so what is the question here? For a bipolar junction transistor, which of the following statements are true? Okay, and there are four options. Doping concentration of emitter region is more than that in a collector and base region. Only electrons participate in a current conduction. The current gain beta depends on temperature. Collector current is less than the emitter current. And these four options are there, and we have to choose the how many are the correct one. So first of all, in the bipolar junction transistor, okay. So I think bipolar junction transistor you have already seen these things. There are three types of like CE, common emitter, common base, and common collector. This type of bipolar transistors are there, but so many times we can have the CE type mode, right? Common emitter type mode. Now here, first of all, we will just go to the one by one options. So first one is what? Doping concentration of emitter region is more than that in collector and base region. So in that transistor, what is there? Let's say it is like emitter, base, collector. So obviously the properties of emitter, base and collector is like that. The emitter area is little bit more than collector, and base is the very small. Base is the smallest part among these three parts. Okay. And one more condition is there. IE is IB plus IC. So you can see here the first option was doping concentration of emitter is more than that in collector and base region. Obviously it will be correct one because the area of the emitter is little bit more than base as well as collector. So the doping concentration on E will be more than B and C. So the first option, whatever it is given, that is correct one. The doping concentration for emitter is greater than base as well as collector, and the doping concentration of base is smallest compared to E and C, and the C will be the middle doping concentration. I mean, like, it is not that much as E, it is not that small as B. Okay. So the first option will be the correct one. Doping concentration of emitter region is more than that in collector and base region. So this is the correct one. Now coming to the B option. Only electrons participate in current conduction. Is this correct? No. Because in transistor, electrons as well as holes, these two are participating equally for the electron conduction and current conduction. So only electrons cannot participate in current conduction. The holes are also participating in current conduction. So this option is not correct. Now coming to the C option. The current gain beta depends on temperature. Now coming to current gain. What is current gain here? If I take CE mode, then what is current gain? Let me write it as beta, and what is beta here? Beta is nothing but IE by IC or IC by IE. I just reversed that. It will be IC by IE, the collector current, the ratio of collector current and E. The ratio of collector current and emitter current when there is a condition also, when VBC, that means base to collector voltage is constant. Okay, so this is nothing but beta. Now in that question they are asking that the beta depends on temperature. Is it correct or not? Beta depends on temperature. So like you can see here, beta is nothing but the ratio of two currents. One is IC and another one is IE. So if by anyhow I can show that IC is depends on temperature or IE is depends on temperature, then we can see that obviously beta is depends on temperature, right? So how to do that? Like, I don't know that IC and IE which one depends on temperature. We have to check. Like, IC is depends on temperature or IE depends on temperature, right? So first of all we will talk about IC, right? So there is one expression. It's a very simple expression that we can write IE as IES. This is the saturation current, right? Emitter saturation current into e to the power VBE divided by VT minus 1. What is T? VT is thermal voltage. Thermal voltage. And it can be also written as KB T divided by Q. Now you can see that there is one temperature is there. That means in VT there is one temperature. Now if I just put the value of VT here, then what will have? It will be like IE will be IES e to the power VBE divided by KB into T, and there is Q, then minus 1. Now you can see here that IE depends on temperature. And how it depends on temperature? See, if temperature is increasing, then our VT is increasing. If VT is increasing, as a whole this term is decreasing, right? If it is decreasing, then obviously IE is also decreasing. Okay. So if T is increasing, IE is decreasing. Okay. So if T is increasing, IE is decreasing. Now coming to beta. Beta is what? Beta is IC by IE, and VCB is constant. So now you can see that if in T increasingness, IE is decreasing. That means our beta will be increasing here, right? I am not talking about IC right now. I mean how IC is depends on temperature. That I am not talking. I will talk a little bit later. But from this scenario, you can see that beta is increasing when temperature is increasing, right? So when temperature is increasing, at that time beta is also increasing. Okay. Now coming to the icy condition. In general, we can say that if T is increasing, IC is also increasing. If it is the case, then you can see that beta is IC by IE. At temperature increase, when temperature is increases, IE was decreasing and IC is increasing. So obviously, as a whole, beta will be increasing, right? So whenever it will be there, is it IC or is it IE T dependency? I can say as a whole, the result will be like when T is increasing, beta, that means current gain, is also increasing. So and also vice versa is there. That means T is decreasing, beta is decreasing. So as a whole, I can tell that beta, the current gain, depends on temperature. Okay, so this is correct one. I have just explicitly expressed that how we can say this one, but you can, whenever in competitive exam, whenever the questions is like that, you just remember that one, that beta depends on temperature. So whenever that type of questions is coming, then we are just going to write that, okay, current gain beta depends on temperature. Now coming to the option D. Collector current is less than the emitter current. Okay, is it correct or not? So I have already written here one expression that IE is equals to IC plus IB. So what is the meaning of that? You can see here that IE is emitter current, IC is collector current and IB is base current, right? So IC is less than IE from that equation because there is a IB term and IB is not equals to 0. So if IB is 0, then we can say that IE and IC are equal. But it is not in the case. The real case is like IB will be 0. But in the, pure case. But in the real case, IB is not equals to 0 and IC is less than IE. Okay. So that means in the CE mode transistor current, bipolar transistor, IC, that means collector current, is less than IE. Collector current is less than the emitter current. So this option will be the correct one. Now how many options are the correct one here? You can see here that A option is correct, C option is correct and D option is correct. Okay. So these three are correct. I think I lost it in my internet, right? Okay, so this is the case. So that means for this question, the right answers are A, C and D. Okay. I know today my internet is not that much good, so that's why it is deconnecting and all, but no problem. I am recording the screen, so it will be visible. When I will upload the video, then you can see that one also. Okay. So have you heard this question or not? I did not feel that when the internet has gone. So hello, can you hear me? Hello. Okay. So I did not understand that when the power has gone. So Have you heard that one that I was explaining that question number 28? Yes or no? Okay, so I'm going to, I think it's already explained and it's already recorded, so I think after the class also you can see that one. So I'm going to the next question right now. Sorry, I think you did not hear that properly, but yeah, like you can see that in the recorded session. Okay, but otherwise you can see right now also this is very simple that for a bipolar junction transistor, how many statements are true? So I have explained here that among these 4 options, 3 options are true: A, C and D. What are the options here? Doping concentration of emitter region is more than that in collector and base region, and the current gain beta depends on temperature, and the collector current is less than the emitter current. These 3 options will be correct one. Okay, and how these 3 are correct one I have just explained there, and you can see next later also. Okay, so now coming to the next question. Next question is what? This is also coming from the GATE 2022 question paper, and we are talking about question number 59. Okay, so what is question here? The question is the minimum number of 2 input NAND gates required to implement the following Boolean expression is what? Like how many NAND gates are required, minimum number of NAND gates are required to implement the following Boolean expression. And the following Boolean expression is given as y equals to a b bar into c plus bd plus a bar b bar whole into c. Okay, so this is the Boolean expression, and we have to know that how many number of NAND gates are required for that Boolean expression implementation. And also you can see there is important thing is there is written as 2 input NAND gates, but you can see here in that Boolean expression there is A, B, C, 3 inputs are there, but they are asking about 2 input NAND gate. Can you hear me? Can you hear? Hello? Okay. I thought I was disconnected. So there are 2 input NAND gates in that question they are asking. But you can see that our Boolean expression is like that. There are 3 inputs given, A, B and C. Oh, obviously D is also there. Sorry, I did not see that. So D is also there. So what I will just make this one a little bit simple. Okay. So how to do that? I just going to write that A, B bar, C plus BD, then plus A bar, B bar, then as a whole C. Okay, so this is the Boolean expression, and I am going to simplify that one a little bit. Okay, so how to simplify that? Today it's too much problematic. Yeah, I hope it is visible. Okay, so I am going to simplify that one. How to simplify? A B bar C plus A B bar B D plus A bar B bar as a whole C. Now obviously B bar is there, that means this will cancel out. So which one will left? This one, A bar B bar as a whole C. Then it is not there or what? Okay. Now see, A B bar C C, A bar B bar C. So A B bar C C, that means it will come as A B bar C plus A bar B bar C. Now you can see here B bar C we can write as common, then A plus A bar. Then what will be the answer? B bar C only. Right? So I think the Boolean expression is all of you knows these things, like how to cancel, like a plus a bar will give us 0 or 1 value, then b bar it will give us 0 value. So like that, this type of this type of properties are there. Okay. I'm really sorry, but it will be recorded. You can just see that one later also. So this is the simplified version of that Boolean expression whatever we were talking about. So you can see here I just did like that, y equals to this one, and then I just explicitly explain that one, that just express like a b bar c, then the simple calculations is there. Now you can see that b bar is there, that means from the Boolean expression law we can see that this one will be vanished, and then you can see like that. Then here also like cc is there na, so cc will come as c. This is also a Boolean expression, right? So then we can write here as a b bar c plus a bar b bar c. Now you can see here that a plus a bar is there, and a plus a bar will give us 1, so that means there will be only b bar c. So you can see here that our Boolean expression whatever it was there, it can be simplified as b bar c, right? Now this is not the question that we are going to simplify that one. The question is how many 2 inputs NAND gate will be written and will be required for this Boolean expression. So how many NAND gate will be required here? So how many NAND gates will be required? So we will do that. Let me write here one thing. See, here b bar is there and c is there. So that means one input should be b, and it can be go as like this in NAND gate. So if it is b, then what will be the output of that? This will be b bar, because here is b, and it will be like b whole bar. So b whole bar means it is b bar. Okay, so this is b bar. Now this b bar is going as an input for an AND gate, and let's say this c is going as an input. So what will be the answer here? The answer will be b bar c whole bar. B bar is the input and c is the input. B bar c whole bar. Now this whole I can just put as as in a NAND gate. Then what will be the answer? B bar c into b bar c whole bar. Right? That means what will be the answer? B bar c, it will come as only b bar c. This b bar c, this bar, yes. Anyone have any question? Let me see. Who has question? Do you have any question? Oh. Someone has question? Oh, sorry, I can't hear you. Can you tell me? I have written B bar C twice. This one?
This one was.
No, yeah, I will tell you. Okay, just wait, let me write. See, this is our output from this gate, right? The gate is what? That B bar was there and the C was there, so as a whole it will be bar. That means B bar C whole bar. This is the output from this gate. Now we want this one. So we want this one means let me tell you, this is as A. So this is A bar, but we want A. Then what should I do? This A bar I am putting as double input for that another NAND gate. So if I am just putting that one is another NAND gate, then let me check. This one is A bar, this one is A bar. So the output will be what? A bar A bar whole bar, right?
Yes, ma'am. It is fine.
Yes. So a bar I can write it as a bar, and as a whole it is a bar. So that means it is nothing but a. So similarly, I have written here that a is nothing but b bar c. So that means b bar c is here, b bar c is there. Sorry, b bar c whole bar, b bar c is whole bar, and as a whole that answer will be b bar c. Now you can see that how many minimum number of NAND gate we need for this Boolean expression. 3. Because there is not that much, I mean it is the minimum one. We can't make a type of Boolean expression like b bar c without 3 at least. So that means the minimum number of NAND gate will be 3. So the answer, whatever it is there, the minimum number of 2 input. Why 2 input is given here? You can see the output in that Boolean expression. If I just see as a lemon side, then you can see A, B, C, D. There are 4 inputs, but we don't need 4 inputs. There should be only 2 inputs is enough. Only B bar C. Okay, so this is 3. Okay, so I hope it's understandable. Then we will go to the next question. Yeah. So next question is also from the electronics topic, and there will be 2019 question paper, and the question is 28. Yes, this is question 28. So what is this one? Now see the question first. Consider the following Boolean expression. There is a Boolean expression, and it can be represented by a single 3-input logic gate. Identify the gate. Okay. So what we will need to do? First of all, let me write it as y. And what we will do? We will just simplify this y. Okay. So first, I am just going to write it y as a bar plus b bar, then a b plus c whole bar can you see? Okay, good. I thought my internet has gone. Plus a b bar c bar plus a b bar plus c bar. This is the expression. So this is a NAND and NOR and what is that option? And or XOR and NAND gate. Which option is this one? So we have to check that. So first of all, we will just simplify that one a little bit. How to simplify that? Just calculate with me. See A. Okay, I am just writing here A bar plus B plus C whole bar plus A B bar plus C bar. It's too much fluctuating. Sorry for this interruption. Okay. So A bar plus B bar, then A bar plus, you can see here I can write it like B bar into C bar plus A B bar plus C bar. Then how to write it? Like A bar plus B bar, A bar plus B bar C bar plus A B bar plus A C bar. Right? Now you can see that A bar is there. So that means I can write here one A bar. Then A bar B bar C bar plus B bar A bar plus B bar C. So that means B bar C bar plus A B bar plus A C bar. Right? Now you can see here. Okay. So A bar B bar A B bar. So what I am writing here, I have to simplify that one, right? So B bar C bar plus A C bar plus, you can see here B bar A bar. So that means this B bar we can put as a common, and A plus A bar is there. So A plus A bar is giving as 1. So that means simply this B bar. Then A bar plus B bar C bar 1 plus a bar with these two, right? A c bar plus b bar. Then what will be the answer? A bar plus b bar c bar plus a c bar plus b bar. Now you can see here a bar, b bar is there, c bar plus 1 plus a c bar. Then a bar plus b bar plus a c bar. Now again I can do something here. A bar, let's say 1 plus c, I am just multiplying, plus b bar plus a c bar. Then what will be the answer? The answer will be a bar plus a bar c plus b bar plus a c bar. Oh no, let me write it c bar. C bar. Okay. So then a bar plus b bar plus c bar, a bar plus a. Then what will be the answer? A bar plus b bar plus c bar. It can be written as a b c whole bar, right? So if it is a b c whole bar, then what is this one? This is nothing but 3 input NAND gate. Is it fine? Because a b c, these three are inputs, and NAND gate if I write, then ABC whole bar. Can you understand? Anyone is there? Okay. I think I got lost. So the answer is NAND gate ABC whole bar. So the answer will be D option. Okay. So answer will be D option. This will be NAND gate. Okay. Is it fine? I think yes. Because we have just explicitly explained the terms of y. Nothing else. And we end up with one expression that ABC whole bar. And ABC whole bar is nothing but a NAND gate. So that's why we can write, it can be represented by a single 3 input logic gate which is NAND gate. Okay. Okay, so we will go to the next question. This question I have taken from GATE 2018 question paper, and the question is question number 13. In a 2-to-1 multiplexer as shown below, the output X is A0 if C is 0 and X is A1 if C is 1. Which one of the following is the correct implementation of this multiplexer? Okay, so first of all, I think it's simple that what is multiplexer. For multiplexer, you can see there are multiple input and there will be one output, only one output. Okay. So, what will be the output for this case? It is written the condition here. X will be A0 if C will be 0. X will be A1 if C is 1. Right? So then what is the what is the current X I can write? X is A0 if C is 0. X is A1 if C is 1. I think this is the case, right? Yes. So now, these two condition I can write it as one single line. X is A0 C bar plus A1 C. Why? Let me see C equals to 0. If C equals to 0, then this term will be 0. And this term here it will be 1. And if 1 is there, that means it will be A0. So that means if C will be 0, that X will be A0. Now come to C will be 1. If C is 1, then this term will be there and this term will be vanished because C bar is there. So that means it will become as 0. Right? So X will be A1 for C equals to 1 case. Good. Now we have made one expression of X. A0 C bar plus A1 C. Now come to the Boolean expression here. Boolean logic gates here. Our X is A0 C bar plus A1 C. Now let me take any one of the option. Let me take this one first. A0 is there, C bar is coming here, and this is AND gate, so A0 C bar. A1 is coming, C is coming, A0 C, and this is OR, so that means A0 C bar plus this is A1, A1 C, so it will be A1 C. Now you can see that this is exactly matching with whatever we want, right? Our A0 is coming, C bar is going, A0 C bar, then C is coming, A1 is coming, A1 C. As a whole there will be a one OR, then X will be A0 C bar plus A1 C, this one. So the correct option is A. Now coming to, obviously we got the correct option, but let us take the D option here. So D option will be what? A0 C, A1 C. So it will be A0 C plus A1 C, which is not exactly the correct one, what we want. Okay, so this is not the correct one. And obviously you can see for B and C also, this will not give the X whatever we want. Okay, so the first option was the correct one, where X is A0 C bar plus A1 C. Okay, now we will go to the next question. If it is understandable, I hope it is understandable. Okay, now coming to the next question. Okay, so this is the next question. The next question is from 2018 question paper, and the question number is 11. The logic expression A bar B C plus A bar B bar C plus A B C bar plus A B bar C bar can be simplified to what? Okay, so we will write this one. First of all, we will simplify that one. Y is, let's say, A bar B C plus A bar B bar C plus A B C bar plus A B bar C bar, A B bar C bar. Okay, now I am just going to write it like that. A bar B bar C plus A B C bar A B bar C bar. So you can do one thing. From these first two, we can take common like A bar C, B plus B bar, plus from the second, last two, I can common it like A C bar, B plus B bar. Okay. Now you can see here it can be written as A bar C plus A C bar. So this is what? A bar C plus A C bar. A XOR C. A XOR C, if it is like that, then what will be the Boolean expression for A XOR C? A C bar plus A bar C. Which one is the correct one? So the correct option will be A XOR C. A. Okay. I think it's understandable, right? So this is the question number 11 from GATE 2018 question paper. Okay. So these are the total 5 questions. I hope there is no other questions. Yes. These are the total 5 questions we have taken from GATE previous year question papers. on electronics topic. So if you have any question regarding these 5 questions, you can ask me. I am just going to repeat these questions again so that it will be like you can see these things. Okay, so this is from GATE 2023 question paper, and the question is this one: which one of the following options is correct for the given logic circuit? And someone has already written that one when I just did that one. So the correct answer is D. Now coming to the second question, GATE 2022, and it is question number 28. For a bipolar junction transistor, which of the following statements are true? Doping concentration of the emitter region is more than that in collector and base region. Only electrons participate in current conduction. The current gain beta depends on temperature. Collector current is less than the emitter current. Among these 4 options, A option, C option and D option will be the correct one. Okay, like dopant concentration of emitter region is more than that in collector and base region, it will be correct. The current gain beta depends on temperature, that will be correct. Collector current is less than the emitter current, that will be correct. Okay, so this is MSQ type question and there will be 3 options correct. Okay, so now coming to the third question. I have taken this from GATE 2022 question paper. Question number is 59. The minimum number of 2 input NAND gates required to implement the following Boolean expression is 3, and the Boolean expression is y equals to a b bar into c plus bd plus a bar b bar c. Then the minimum number is 3, and I have drawn that expression also, like that gate implementation also I have written here. Now in this fourth question, I have taken it from GATE 2019 question paper, and the question is question number is 26. This is this is fourth question. Consider the Boolean expression. I think I have taken 6 questions. Okay, I have taken 6 questions. So consider the following Boolean expression. It can be represented by a single 3 input logic gate. Identify the gate, and the gate is NAND gate, and the Boolean expression is a bar plus b bar whole into a into b plus c whole bar plus a into b bar plus c bar. We have just written there that one and simplify that one, and we got the answer as a plus a b c whole bar, and a b c whole bar means it is NAND gate. Okay, so we are getting. Now this is the last question. It is taking from GATE 2018 question paper, and the question is, oh no, this is not the last one, this is the 5th one. It is question number 13, and in that question number 13, in a 2 to 1 multiplexer as shown below, the output x is a0 if c is equal to 0 and x is a1 if c equals to 1, a0 a1 c, and the output is x. Which one of the following is the correct implementation of this multiplexer? And we did that one and we got the answer that A will be the correct option, where the output will be in the form a0 c bar plus a1 c. Okay, now coming to the last question. This is I have taken from GATE 2018 question paper, and the question number is 11. The question is the logic expression a bar b c plus a bar b bar c plus a b c bar plus a b bar c bar can be simplified to which option? You can see here, if I simplify that one, then the option will be a c bar plus a bar c, and a c bar plus a bar c is nothing but a XOR c. Okay, so that means the correct option will be A. So these are the 6 questions we have taken from previous GATE questions and on GATE electronics topic. So if you have any question or doubt, you can ask me. I think I lost my internet. Okay, so these are the 6 questions we were talking about, and yeah, so this is for today, and if you have any question you can ask me or we will meet in the next class. and in next class we will talk about some different topic. Okay, so till then, okay, bye, and we will meet in the next class.